Should I start? Should I start? Hello? Hello?
Yes, you can start.
Can I start? I can start now? Yes. Okay, thank you very much. Can you hear me clear? Yes. So, yeah, hello. So, thank you very much for organizing this wonderful conference, and pardon me for not being able to be present in person. Hopefully, I will visit it physically in the near future. And so, yeah, so this Shukran Zazilan, thank you very much, and NYU Abu Dhabi for this opportunity to speak at this QIQ Matter seminar conference. So my title will be Ultra Unifications. And for the first part, and quickly, the second part will go to categorical symmetry of a standard model from gravitational.
Sorry, Juven, sorry to interrupt. Can you raise the volume of your microphone there? Because it's very faint.
Okay, sure.
To maximum, please.
Yeah, let me see what the. Can you hear me clear? More clear now?
It's better now?
Better now, yeah.
Is it max? The echo is temporary. We're gonna mute ourselves here. No, no, echo is always. Okay, let's try it.
So is it better now? Hello? So should I continue?
No, I think it's okay.
Okay.
So now it's only on my laptop. Because if I connect it to Zoom, then it has the echo.
Okay. Okay. So the slides are downloadable from this website idea.info, and this will be based on work collaborated with Pavel Putrov, Zeying Wang, and Yizhuang Yu. So just make sure. So if you imagine that you're going to play a chess game and see the chess man on the board, every piece is on the board except this one. And what would you guess the missing piece it is? You will try to find this one. So the question here is like, if you just look into the chessboard and with a chessman like this, if you never really played chess before, you will just try to look at the reflection symmetry with respect to this axis. There's some rook here and holds the knight and bishop, and they are reflection symmetric. So you might guess there's a left-hand side king. There should be some right-hand side king, right? So coincidentally, there is some analogy that you can also do for the so-called elementary particle in particle physics, that quarks and leptons you can draw, for example, in one family or one generations. They are up and down and three colors, SU3 fundamental, and there are some SU2 doublet, for example, for the lepton quarks. There's also the lepton sector, the neutrino and electrons, and there are 8 of them on the left-hand side. And similarly, there's a right-handed particle, which we draw right-handed antiparticle here. And they also have the SU3, three-color triplet fundamental, and also, however, they are SU2 singlet, and there's also right-hand electrons. And what is missing in this table is exactly the stereo right-hand neutrino. So we can ask where is the missing stereo right-hand neutrino, just like we are asking where is the missing right-hand king. But as you know, in the chess game, the queen is the one that fill the spot. It's not a stereo right-hand king. So we can ask the same thing. Maybe we are identify some elementary particle we think the right-hand neutrino wrongly. Perhaps there could be something else replace the stereo right-hand neutrino that we find so hard to identify the existence. So what is being called ultra unification, proposed 3 years ago, is about some nonperturbative global anomaly, some people call discrete anomaly, that cancellations involving baryon minus lepton type of symmetry that I will explain permits to replace some of the zero-dimensional elementary particle excitation right-hand neutrino in the 4D standard model quantum field theory vacua, replace that with a fermionic version of the some 4D or 5-dimensional topological quantum field theory, or TQFT, or possibly interacting conformal field theory sector. So this is a proposal, and that's the idea. So is this analogy clear? So let me make some introduction before we go to field story. So as we know, standard model is something you learn from textbook. And this field gap that we are applying some of the knowledge people here in quantum matter and quantum info to say that whether we can use those development to say something, address some problems in also the quantum theory, quantum field theory in our vacuum, the standard model. That's the main purpose of the talk. And in my talk, we require the confirmed 15 Weyl fermions per family, and possibly plus or may not be there for the right-hand neutrino, and with 3 families. And here we draw in cartoon pictures the Weyl fermions in this some representation of SU3, SU2, U1 are written here. And detail is not so important. I will just point out which is important for you. And each of this disk is actually the Weyl fermion, which is 2-component complex fermion in the fundamental of the SU2, which is the subgroup of the spin 3,1 more precisely. So these are the space-time symmetry, okay? And we have already confirmed a lot of the things in the standard model, like a gauge boson. There are gluons, 8 of them, and 3 W plus and minus Z0, and also the U1 hypercharge gauge bosons. And there's a U1 EM photons. There's a spin 0 Higgs boson, and there's a spin 1 gauge bosons, and top quark is also found, and Higgs is also found. So what is missing in the table is exactly the stereo right-hand neutrino. And if we pull further, we should multiply by 3 families, and there are some tables of this quantum number. But what I want to emphasize and look into that is, as we know, most of the so-called anomaly cancellation in the standard model is quite good, involving this gauge group. But including additional symmetries, which not seem to be gauged at the scale of a standard model, the B minus L, or more precisely, this quark minus NC color number, lepton number, these are probably good quantum number and almost like good classical type of symmetry. And also another version other than B minus L is the B minus L combined with hypercharge, this so-called X symmetry. So this has this quantum number. So we will look into this this quantum number, this symmetry, and the cancellations of the anomaly within the context of the standard model, and checking the local and the global anomalies from the angle of index theory and Cobordism. So this is what we'll do for the first part. And let's look into this 3 family carefully. As we said earlier, that the 3 right-hand neutrino are not found. So if you want to label that anomaly index within the standard model, you will see the important index is the number of the family or generation in the standard model is presumably -3, plus number of the right-hand neutrino. If some of them are there, some of them may not, this index will be 0 and 1 for the neutrino number for each family. So this number may not be 0 in the standard model. Actually, it should be just -3 in the standard model. So one story, possibly some of the people here also aware, is that the recent development in the condensed matter tell us that the anomaly cancellations can be cancelled by some more subtle way. For example, in 3+1 dimensional topological superconductor protected by anti-unitary time reversal symmetry, this is the bulk, and we are drawing the fermionic spectrum in the momentum space, so-called dispersion relation, like a Brino zone dispersion. And the free fermions is a possible boundary state, so known as the massless Marana fermions, can preserve time reversal symmetry. So these are the gapless dispersion. But it could also be gap, in which Marana mass term can break time reversal with this gap dispersion. And what condensed matter folks find summarized, for example, in this review, saying that actually there could be some topological TQFT field theory or conformal interacting field theory to saturate same type of anomalies, that is some of nonperturbative global anomaly, typically not captured by Feynman graph. So one particular example known as the Z16 class, and this Z16 class topological superconductor is realized, for example, in helium-3b phases, and it's also written mathematically as 4D Atiyah-Pardo single eta invariant. And this anomaly cancellation involving this TQFT sector, some people call it Green-Schwarz topological version of that Green-Schwarz mechanism. So we are going to do one higher dimensions, which means we are going to do the 4+1D theory. 4+1D bulk, and where the boundary is 3+1D, that presumably have something evolving standard model. And in the case of having the baryon minus lepton discrete type of symmetry combined with some hypercharge that I denote as X, this discrete version of this B minus L actually is robust and is respect even the multi-fermion, 4-fermion interactions. And this is a unitary in contrast to the time reversal, which is anti-unitary, but it's a discrete as well, this symmetry. And this symmetry has similar property, that square of that is fermion parity. And we can also ask the same thing, say if there is such a bulk state, what are the possible boundary? And immediately you will come up with, there could be a Weyl fermion massless one, or gap fermion with Marana mass, or pair with Weyl fermion with Dirac mass. And this will break X symmetry in some way. However, what the earlier slide and also this information from condensed matter people are saying that it's possible to have a topological field theory sector as well, CFT sector as well to cancel the same anomaly. So what the right-hand neutrino actually exactly carry this type of anomaly, and we can people hypothesize that they can get some Marana mass pairing between the right-hand neutrino itself, or could get Dirac mass by pairing with left-handed neutrino. But since we haven't found right-hand neutrino, so the part of proposal here is that perhaps we do have a different mechanism for neutrino. We might need to replace the right-hand neutrino or the right-hand king to a queen, which is like a TQFT CFT sectors. So this is the idea. So we can also write down this 5D bulk more precisely as the eta invariant, as the Poincare dual or some this Z4 Z2 gauge field pair with this 4D eta invariant, and it can be decorate construction by putting this 3+1D topological superconductor on the X symmetry breaking domain wall and try to condense that. So there is some condensed matter understanding, and this symmetry has been discussed since Weyl and Z, possibly also Weinberg around the same time, and people has been study this type of invertible field theory or topological superconductor or phases, including one of the participants, Chang Zexie, and our work. Okay, so if you are following me, then the proposal of this Ultra Unification is saying that we have a quantum field theory of standard model or even granular theory sectors coupled into this topological quantum field theory or conformal field theory sector, which may behave on part of the beyond standard model sectors of a dark matter sector. And the two sectors now talk to each other through discrete B minus L gauge forces. In the scale of the standard model or below, the electroweak scale, this might look like a global symmetry. But these can be gauged at high energy, so there is some discrete gauge forces. But because it's discrete, so there's no propagating photon spin one B minus L photon. But you only have some topological interactions. So the interaction is something like a statistical braiding process between the lines and observable operators in one side with the observable some line and surface on the other side. Okay, like a Horner bone type of interaction. And the whole system are meant to cancel some global anomaly, and for example, the Z16 class. And these are involving the gauge B minus L and gravitational type of anomaly. Okay, so this is the idea. And we should put this quantum field theory coupled to TQFT CFT generally on some curved space-time on the gravity. But the gravity here we discuss is not full quantum gravity, so it's still some kind of semi-classical dynamical gravity. And there's such an analogy in condensed matter known as Lipschutz multi-theorem. In fact, in condensed matter community, people like Subir Sachdev and possibly also participants like Subaru Bhattacharjee, they possibly study these type of things. They study this condensed matter pseudogap phases in high TC, and for example, Subir particular proposed there's a hidden topological order sectors. So in that analogy, in my case, is that the standard model may contain a hidden topological order TQFT CFT sectors, are just meant to cancel some anomaly together. And if I want to make some illustration by thinking about the quarks and leptons in our body, which evolve in U and D quarks, and the electrons surrounded the nucleus, they do have a B-SL gauge charges, so they can be the charge endpoint of some B-SL Wilson line. And such this B-SL Wilson line can connect to the hidden sectors, where the lines and surface operator may form some kind of linking very schematically. They can carry the same B-SL type of gauge charges. So there is some kind of a topological interaction between our sectors, the quarks and lepton, somehow wired, presumably wired, and interact remotely through topological interaction with these hidden sectors when the B-SL become dynamically gauged. So this is the kind of way. So putting into the words like we may be living on the neighbor of either 4-dimension or 5-dimensional topological quantum computer medium, just like Guanyu Zhu, the participant here study, this type of things. Topological quantum computer is actually neighbor to us, and we are wired connect to them through this discrete B-SL forces. So this is very cartoon way of saying that. And if I show more detail, then what is in the ingredient in the left-hand side is the 40 stand model with 15 times 3 or index minus 3 mod 16 of the these sectors, evolving more conventional Young-Mills, Anderson-Hicks symmetry breaking or gauge symmetry breaking, Weyl fermion Dirac mass, and described by characteristic class fiber bundle. And the missing piece of a right-hand neutrino may or may not be there for some family, but the hidden sectors is describing by TQFT non-invertible or invertible in 4D and 5D, and construction involving something called symmetry extensions, and there are tools like cohomology, Cobordism, and category to describe them, and the mass mechanism can be also very different, more interacting, and there are possible CFT sector as well, and altogether I'll talk through topological interactions, and they are meant to cancel this global anomaly. The construction might evolving more lines and surface operator, which people love to study, but now there's a purpose to study them for BSM, and they are constructed also from this off-Brown cavalry or Vidovsky-Kitaev type of Marana chain invariant. So this is a cartoon picture how these things talk to each other and put it together. So in one slide, then I usually imagine a standard model living in in the contents we are familiar, and now they are neighbors exactly in the same vacuum, but either in the 4D, the same neighbor as we do share the same space-time, or we are living on the boundary of that. And there are some anomaly cancellations, index cancel, and there are some bulk terms. And this is captured by Cobordism class. But the main point is that once the stereo neutrino is missing but carry a z-sitting anomaly index, then we can replace it by other highly interacting TQFT or CFT sectors. Okay, so we are basically almost done for the first part of my talk, and which basically try to combine standard model with TQFT sectors or CFT sectors. And I'll be more precise in the next few slides about these anomalies, and which evolve in the perturbative local Z square, Z class, 2 of Z class, and 1 of Z sitting class. We'll briefly go through the index theorem, which Schreiber will be very familiar, captured by characteristic classes, and Cobordism, which we check further. And then we will just quickly summarize this proposal. And then the second part of my talk will go to saying that if we remove those hidden sectors and just look into standard model, in fact, it does has this anomaly, but we can, using some recent development, try to interpret this anomalous symmetry as revive the anomalous symmetry as non-invertible. The anomalous invertible symmetry, part of it can be revived as non-invertible categorical symmetry, and we'll go to that. Quickly review possible QD example and then go to the standard model example. So this is outline. So you have learned that the baryon minus lepton actually has anomalies even at the Feynman diagram calculation show that the B-SL suffer from gravitational anomalies. Once the number of the family and the neutrino number are not matched, and the lepton number current will not be conserved. And same for the B-SL cube type of this anomaly. And this has indication saying lepton might be generated through the gravitational instanton. So this will be called leptogenesis through gravity. But some people will be more conservative, say perhaps these are just some accidental symmetry and with some low energy Tahu anomaly. Or perhaps people will just say we can just aid this stereo right-hand neutrino. In fact, this is most of the case before what the proposal of ultra unification. People mostly just do this. The thing I want to emphasize that we do have scenarios, new scenarios to cancel or to do something else, and this will be a BSM window. So anomaly polynomial is the way to capture the anomaly, which is written for the anomaly in 6D form. And learning from Atiyah single index theorem, there is a A-loop genus of space-time tangent bundle and written as conjunction classes. And in the most important part of my talk is just P1, which has trace R wedge R of some curvature 2 from R. And also character of the train character written by some train classes. And we should put in the Weyl fermion in suitable representation for this complex vector bundle and try to compute this. And the outcome of this will be this 6D anomaly polynomial with all the data from the standard model fermions. Okay. And this is actually one formula is enough to summarize many computations you can do for Feynman graph. And what the end message is that just this B-SL gravity square and B minus cube. And possibly if you change to SU5, there's also the the SU5 was the SU5 was this B-SL X symmetry. This anomaly may not cancel with 15 Weyl fermion. So this is the thing we are emphasizing earlier. If we want to write it more in the more familiar current conservation way, then we can check the current from the quark number and lepton, which is B and L related. And some of the combinations like B-SL is basically conserved within the gauge sector of U1, SU2, SU3, but not conserved under turning on background dynamical gravity. Okay, so this is exactly the tool of the Feynman graph capture for this non-conservation of this B-SL like current, and the precise non-conservation is exactly related to this index of the family and the right-hand neutrino number difference. Okay, and we can write this the 4D anomaly as 6D anomaly polynomial as well as written as 5D invertible topological field theory. So this will be the 5D term. Okay. So what we are going to do next is that we want to confirm this index theory and calculations indeed is also true holds for the Cobordism including interaction. So this is related to what the Robert John Slager talking about this case theory free fermion class occasions. But now including Cobordism, we will see that indeed such a class of the Z square will still be there when the B-SL symmetry is still a U1. However, if we break down the U1 B-SL down to some discrete Z4, as we advertised earlier, then this will become a Z16 class, and which become a global anomaly. Okay. So yes. So what the Cobordism check here, given in this reference, using free Hopkins Cobordism calculations, showing that given the standard model data, indeed most things are canceled as it should. And we don't really have too much room other than just the Z square and Z16. There are a few other cases, and I'm not having time to talk about other cases, but I'll focus on this Z and Z square. There's also some other Z2 choices you can play a role for BSM physics, but today we'll focus on this Z and Z16. But the point is that Cobordism actually say the index theory actually capture most we need, except the Z class will break down to Z16 when you break the U1 B-SL down to Z4. Okay, so what we are going to do is saying that let's just remind ourselves if the anomaly is not cancelled, what does it mean? In the usual case of an anomaly matrix, say suppose there's an anomaly index as should preserve in the sense of under energy RG flow, that at high energy there's such index and possibly capture within some symmetry, and you compute the index. And when you go to IR, it could be symmetry breaking phases, but you can still compute the index in some way. And you could possibly symmetry preserve with some gapless fermions or even interacting CFT. But if the index is non-zero, then you cannot have a symmetric gap phases. That is with no anomaly, such is known as symmetry mass generation. It's not possible for that. But it could be symmetric gap TQFT, and some people call topological mass generation. It's possible only for some global anomaly. Okay. And this anomaly cancellation, anomaly mention can be replaced as anomaly cancellation if flip the story such that everything add up together to cancel to be zero at some energy scale. And basically, we just repeat this and adding one possibilities of going to one high dimensional invertible field theory. So the proposal is that we can use this all the possibility to cancel the anomaly that is not canceled in the standard model. And in fact, in most of cases in the standard model, like Dirac mass, Weyl fermion is already included in a way to cancel the some anomaly. But what is new is written here. So the green part is the one is within already in the standard model scenario, people use it. But this purple part is something that we can do. We can in fact emphasize this either TQFT, CFT sector can get involved, and also it's 5D bulk. So this is that scenario. So the crucial part of try to summarize what exactly is being used is that we only assume the standard model gauge group and the content of the Weyl fermion 15 times 3, and assume discrete BMI somehow is preserved, not broken at high energy and dynamically gauge at some higher energy scale, just due to no global symmetry in quantum gravity. Then using these three assumptions, basically two is confirmed, and the last one just a mild assumption that you can judge. Then to cancel the anomalies, then we can enumerate the possibility. And these are possibility I draw in cartoon earlier, but right now writing down, other than the standard law of this Dirac-Marana fermion masses, again from stereo right-hand neutrino paired with itself or with left-hand neutrino, then we have these new sectors, which are basically including beyond zero-T particle physics with extended objects and topological sectors or on-particle CFT physics. But right now, the main purpose to adding those sectors to cancel some global nonperturbative anomaly. So this is a summary of the first part. We do have this whole possible scenario play a game, but then the topological forces will be important. And there are some discussion of how to write the standard model coupled to this new sectors. I don't have time to go to that, but involving some TQFT sectors and Decker with some up-brown cavalry chain, and there's something like a BF type of theory, but it need to be fermionic, so it's more subtle. It can be constructed by some generalization of symmetry extension, and they are following up work, but let me not go into detail. And this kind of combined Lagrangian field theory actions shows in the cartoon picture will be the story I mentioned in the beginning. So this done with the first part talk. In the case of showing the forces unification, then here what we need is actually, before even we go to quantum gravity, there's actually topological field theory sectors that we can add in. Sorry, something. Yeah. So yeah, so this is the kind of proposal. Other than the strong electromagnetic, strong electroweak forces, and the hypothetical gap forces, there's a TQFT sectors possibly joining before we go to gravity in the vacuum standard model, beyond standard vacuum we live in. Okay, so I'm done with the first part. I think I still have some time. Let's see.
So you might have to wrap up soon because we're running late on the schedule and we have an event that we have to attend. So perhaps in a few minutes you can.
Yeah, so that's fine. Yeah, no problem. Maybe 5-10 minutes. So yeah, since the slides is downloadable, so that's fine if I don't have time to go through all the detail. For this part, the non-invertible symmetry is that now we go back to look at the anomaly of standard model, and we don't add the new sectors, but we just make the standard model suffer from that B-cell anomaly. And we want to say that this invertible symmetry for this B-cell symmetry in the standard model, actually part of it can be revived and resurrect back to be some non-invertible version of symmetry, and some people call categorical symmetry. So in contrast to the invertible symmetry, which identify the charge operator or some symmetry generator as topological defects satisfy some group-like fusion rule. There's an identification between a group and a charge operator. The categorical symmetry says that the fusion rule of this charge operator is not obey the group law. In a particular version, we'll look at this subgroup of U1, which U1 is R Z, but we'll look at the rational angle Q Z. And there's a map between this commutative monoid of this fusion of this charge operator to the rational Q Z subgroup. And people interested can see this review paper or some work of my collaborator saying this story. And there has been a work done on this other Weyl-Jacqui anomaly for this story, say that the QED has the U1 actual current not conserved due to the vector dynamical gauge bosons, and the actual current will be violated through this FWGF terms. And this gentlemen, my friends, they did some work in last year and try to revive and make sense of this actual current non-conservation by looking at the rational angle subgroup, such that those broken invertible symmetry can be revived by decorating 3D charge operator as 3D version of abelian Chern-Simons TQFT as fractional quantum Hall state that Steve Simon talked about. So this type of things is the way to changing the charge operator in a new form that make the symmetry become non-invertible. And because out of time, I'll just say that the this procedure can be done in a few steps through the Stokes theorem, such that the charge operator the current non-conservations can be basically absorbed by moving this FWGF term to the boundary as some response of a quantum Hall states with some gauge field A of the U1 vector. But this background like U1 gauge field living on the 3D charge operator can be rewritten as an outcome of integrating our non-invertible type of TQFT of abelian fractional quantum Hall-like states with dynamical little a gauge field. And the new operator will become non-invertible in the sense the fusion rule has no inverse and it's actually also non-unitary. And this only works for some rational angle. And there's some story how to summarize them by a few steps to revive the symmetry, and I don't have time to go to detail. To end the story, in the case of standard model, as we emphasized earlier, suffer from this B-L type of anomaly with FWGF C1 square first Chern class type term or P1 trace out Weyl term. We can also revive that by moving this onto the left side and try to make sense of this current non-conservation as a way to conserve in some way. And the gravity we need to consider is not quite the background gravity, because this will just say the theory has some anomaly, the whole anomaly of gravitational type. But we should consider some semi-classical gravity, but not the full quantum gravity, because all the global symmetry either be broken or gauge. So there's some intermediate range we are considered as semi-classical gravity. And with this understanding, then what we do is try to revive what is broken by a gravitational background by decorating the gravitational Chern-Simons terms due to the relation between gravitational Chern-Simons and trace R Weyl term, moving this gravitational Chern-Simons to the 3D charge operators, and try to fix something called fermion anomalies. And this can be done by decorating a certain type of TQFT known as Witten-Rashtikin-Kurov type of TQFT. And two sectors together are meant to cancel the fermion anomaly, such that one sector fermion anomaly contribute from the fermion F captured by the Z class. The other one is related to the chiral central charge of this WRT theory. And there's a table summarize how to fix that fermion anomaly and how this step can be done, such that the new charge operator can be constructed as a non-invertible theory. You'll become topological. You'll be gravitational general covariant and U1 B-L invariant, but it will not be unitary and non-invertible. And this will be a charge operator for non-invertible symmetry. So there are a few steps. Each of the steps is doing this process. So that's it. Thank you very much. So and let me skip this two part. I think let me conclude. Because time was limited, I expect that I don't have much time to talk, but if you have interest, actually some of the talks you can find, for example, in this YouTube channel. I have other stories, and you might heard just the part of the story from the first Ultra Unification and Categorical Symmetry, but there's other proposals using this quantum matter and the nonperturbative quantum anomaly type of ideas to predict some BSM physics. Let me conclude. So we discussed the invertible U1 symmetry of B minus L actually can be revived for some rational angle subgroup become a non-invertible categorical symmetry. And because there's no global symmetry in the full quantum gravity as a folklore in that community, so the fate of these topological defects might have some new implications, and this symmetry either need to be broken or gauged in some way. There could be some other implication like lepton genesis, and the so-called Ultra Unification predicts possible TQLD CFD sector. It will possibly give new way to think about lepton genesis. Yeah, so thank you very much. Thank you particularly to Ishan Sati and was Schreiber for this organizing this wonderful conference, and thank you.
Okay, great. Thank you very much. Thank you. Yeah, we appreciate it, but I think there's no time for questions. We have to run. But thank you so much. But we'll post this, and we'll also make sure we have a link to the channels that you suggested. Okay, it's good to see you. Thank you so much.
Thank you very much.
Thank you. Bye-bye.
Bye-bye.
Okay, great. Thanks, everyone.